Has anyone found it useful to have the recorded videos posted out there for you to watch? So in case you're not around, you can just watch them. Even though they're like dorky videos posted on YouTube, but hey, so in case Blackboard goes down, you could still get to them, right? Okay. Okay, so now that we know from section 12.5 what vector valued functions are, well, they're like perfectly good functions everywhere. We can do interesting things like calculate derivatives and integrals. So geometrically, we can think about derivatives like this. Remember back from Calculus 1, where the calculus teacher drew the graph of some function f and some value of x on the x-axis, and said we would like to find the rate of change of f at this value of the independent variable x. So what we do is we go some increment down the x-axis. We may call that increment delta x. So now we have this chord that goes from f of x down to f of x plus delta x. And then the slope of this chord is going to be delta y over delta x. But delta y is f of x plus delta x minus f of x plus x plus delta x minus x. So in other words, we're divided by delta x. In order to calculate the derivative, we then take the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And we saw that f prime of x, besides being some algebraic calculation, we can interpret that to be the slope of the tangent line at x. Now we're going to use that same interpretation for real valued functions. Now remember what R of t is. R of t is our position vector function. So you got this three-dimensional curve in space. Remember, we're in 3 dimensions. We have the x-axis, y-axis, and the z-axis there. So I've got some curve in space. Then we have some point P on the curve, and we have position function vector R, what we always call it is R, that goes from the origin out to that point P on the curve. And then let's go a little bit further down the curve by adding some increment delta t to t. So here is R of t plus delta t at point Q. So this vector R of t plus delta t points from the origin out to Q. And then you take a look at the vector that points from P to Q. And that's going to be delta R, which is R of t plus delta t minus R of t. Let me pull out my pen here. So then we could then take a look at taking the limit as delta t approaches 0 of R of t plus delta t minus R of t over delta t. And that's going to be what r prime of t is. And do you see that as delta t shrinks to 0, that q is going to coincide with p, and that difference quotient, delta r over delta t, will give you the slope of a vector that is tangential to the curve. So same interpretation as we saw from Calculus 1. So here, this kind of demonstrates that ideal of taking delta t as it approaches 0, so that we get r prime of t, this tangential vector. So what does that tell you about how you can get a vector that is tangential to the curve? A tangent vector, right, is to calculate the derivative of r of t. How handy. Then how can you get a unit tangent, then? What's a unit vector? Magnitude 1. And a vector, and that is tangential to the curve. So hey, why not take r prime of t divided by what? Magnitude of r prime of t. There you go. So here we go. So here's how we calculate the derivative actually. We don't really compute the difference quotient and stuff. We just go through and calculate the derivative of each of the individual components, because each of the individual components of r is going to be some function of t. So we just go through and calculate the derivatives with respect to t for each of the components. Giving you a new vector valued function, which we call r prime. And we also can interpret it geometrically as a vector that is tangent to the curve. We also call it a velocity vector. After all, what's the derivative of the position function? Velocity, right? So you shouldn't be surprised that r prime is the velocity vector at point where, whatever corresponds to t. Okay? So let's do an example. Number 1 here. A couple of easy problems here. So for part A, we've got r of t is equal to t cubed 3t squared and t cubed over 6. And we need to compute the derivative. No problem. We just go through and calculate the derivative of each individual component. Derivative of t cubed, 3t squared. Derivative of 3t squared, 16. Derivative of t cubed over 6, that should be t squared over 2, right? Okay, that's all there is to it. Just take the derivatives of the individual components. Part B, we have r of t equals e to the negative t I hat plus 10 times the square root of t j hat plus 2 cosine 3t k hat. Calculate the derivative. Again, you just go through each individual component, compute the derivative. What's the derivative of e to the negative t? Negative e to the negative t. There you go. That's I hat. All right, then plus what's the derivative of 10 times the square root of t? 5 over root t, exactly. j hat. Plus the derivative of 2 times the cosine of 3t. What's the derivative of that? Yeah, so that would be negative 6, right? So negative 6. So we have minus 6 sine 3t k hat. All right. Anyone cannot read my handwriting? I know I like to use cursive a lot. By the way, I like to use S as in lowercase cursive S to distinguish from my 5s because I find it difficult to write my 5s perfectly like that to distinguish them from S. So that's why I use S or capital S like that. Do they even teach cursive in school anymore? No, not anymore. Yeah, I guess I'm just way too old school, huh? You don't need cursive. You are. I mean, you don't. You use the keyboard for everything, right? And this picture shows a graph of that first function that we took the derivative of. Let me just point something out. Right here. What's going on here at the origin of the curve? It's a sudden change in direction, huh? Do you think that the derivative exists there? And the answer is no. Actually, the derivative is 0. So the derivative does exist, except the function's not smooth there, isn't it? So it's not smooth when there's that sudden change in direction. So if you take a look about midway down the page on page 831, we say that a function r of t is smooth on an interval if f, g, and h are differentiable, which in this case it's true, they are differentiable, but the derivative in this case is 0 at 0, 0, 0, meaning when t equals 0. So as long as the r prime is not equal to 0 vector anywhere on some interval, then you have a smooth curve. So on the interval, maybe that will trap this portion of the curve. That's not smooth. But this portion of the curve is smooth. Everybody see that? But wherever you see there's a cusp, a sudden change in the direction, or maybe there's even a break in the curve or something, like some sudden change in the trajectory, then the function's not smooth. The curve is not smooth, okay? So the derivative will exist, but where the derivative is equal to 0, that's where you have a break in smoothness. Okay? And when you see r prime being equal to the 0 vector, that's where you're likely to see the cusps. Okay? Now, from time to time, it's going to be important for us to find the unit tangent vector. T hat. That's t hat, folks. That's going to be r prime divided by the magnitude of r prime. So if you want a unit vector pointing in the direction of travel, tangent to the curve, well then you have t hat. Okay? So let's take a look at example number 2. We're going to compute our unit tangents for part A of example 2. We have r of t is equal to t squared, 4t, and 4 natural log of t. And of course, the caveat being that t is positive, because can you actually take the logarithm of 0? No. So let's go ahead and calculate r prime of t. So you can help me here. So what's the derivative of t squared? Come on, guys. 2t. Thank you. Derivative of 4t? 4. Derivative of 4 natural log of t? 4 over t, okay. What's the magnitude now of r prime? Meaning the speed. Because after all, that's what speed is, right? The magnitude of the velocity. So, well, let's go ahead and compute that. So we're talking about the square root of 2t squared plus 4 squared plus 4 over t squared. So skip down here. So we have square root of, so what, 4t squared plus 16 plus, 16 over t squared. Now, it would be convenient for us to combine all these terms, get a common denominator, huh? So we could write 4t squared as 4 times t to the 4th power over t squared. And we could write 16 as 16t squared over t squared plus 16 over t squared. So now we can combine the numerator, 4t to the 4th plus 16t squared plus 16. So we can factor out a 4, then we have t to the 4th plus 4t squared plus 4. So that would be what? T squared plus 4, quantity squared, right? Huh? Oh, no, that's 2. Thank you. Yep. That was t squared plus 2. And then divided by t squared. So when you take the square root, then you got what? 2 times t squared plus 2 over t. So then you have t hat. No, that's not tau. Let me try that again. T hat, not tau hat. T hat is equal to r prime of t over magnitude r prime of t. Now, so we have the vector 2t, 4, 4 over t, and then divide it by 2t squared plus 2 over t. So you could leave it in that form, or you can go ahead and divide each of the terms of r prime by the scalar function 2 times t squared plus 2 over t, which we can go ahead and do that right now. Now, we have 2t over 2 t squared plus 2 over t. The 2's will cancel for that one, leaving you with what? T squared over t squared plus 2, comma. And the next one, we'll also have factors of 2 canceling, leaving you with 2t over t squared plus 2, comma. And finally, 2's will cancel, 1 over t's cancel, leaving you just with 2 over t squared plus 2. So there's t hat. It's a function of t. So you want a unit vector pointing in the direction of travel, tangent to the curve. You tell me what t is. And plug that value of t in for each of those components, and you'll have your unit tangent vector, t hat. All right, so, and a similar exercise for part B. I'll let you look at that on your own individually. Same idea. So We just got done doing this problem. Here's a picture of it. Unit tangent vectors point in the direction of travel. Because after all, we're dealing with an oriented curve, right? The orientation is implied by, as we let t increase in value, is how does the curve evolve? Huh? What is the trajectory of the curve? So t hat's always going to point in the direction of the trajectory of the curve, and feet of unit length, tangent to the curve. So you can evaluate t hat at different values for t. Okay? Always be of length 1. All right, here is kind of a laundry list of some properties and rules for taking the derivative. You'll have a chance to practice these on the homework. But first of all, the derivative of a constant vector is a zero vector. Does that make sense? Because remember, for a constant vector, each component is a constant. So when you take the derivative of each of those constant components, you'll get 0 for each of the components. So you have a zero vector as the derivative of a constant vector. Next one, derivative of the sum of two vector valued functions will be the sum of the derivatives of those vectors. Hopefully no surprises for that one. Derivative of the sum is the sum of the derivatives. Number 3 is kind of a product rule that you should know and love from Calc 1, right? The derivative of the product is not the product of the derivatives, but, you know, is the derivative of the first function times the second plus the first function times the derivative of the second. But that is if the one function is a scalar function and the second function is a vector function. Now, if f and u were a vector function, then we would need to deal with either the dot product or the cross product, because that's how we multiply two vectors, right? Either the dot product or the cross product. So each one of those dot product and cross product have their version of the product rule, huh? Do these look kind of familiar? So quite analogous to the, you know, Calc 1 version of the product rule. And of course the chain rule still applies. So the derivative of u of f of t is going to be u prime of f of t times f prime of t. So the derivative of the outer function with respect to the inner function times the derivative of the inner function. All right, so there shouldn't be any surprises here, folks. It's just a vector version of what you learned back in Calc 1. Okay. Now, no one's asked me about division. Can you divide one vector by another vector? You can with numbers. Why can't you do it with no? Well, because we don't. We just don't do. It seems like every semester that you guys are the first class that have never asked me so far about how to do vector division. Doesn't exist. Okay, good. Well, moving on here. Let's do another example here. Number 3. So we've got a vector u, a vector v, and we'll just do one of these things, and you could do the others. Now, for part A, they want us to calculate the derivative of a v of t squared. Try that again, v of t squared. So vector v is the outer function and t squared is the inner function. So we'll say that this is going to be v prime of t squared times the derivative of t squared, which is 2t. So now we just have to calculate v prime. Now if you look in your book, you see that, let me go ahead and write it up here, that v of t is equal to sine of t I hat plus 2 cosine of t j hat plus cosine of t k hat. So when I write v prime of t squared, let me go ahead and say that that's d dt of, and then go ahead and write the components here, sine of t squared, comma, 2 times the cosine of t squared, comma, cosine of t squared, and then times 2t. So derivative of sine of t squared is going to be what? 2t times cosine of t squared, comma, derivative of 2 times cosine of t squared would be what? Negative 4t times the sine of t squared, comma, derivative of cosine t squared, negative 2t sine of t squared, times 2t. And it's customary for us to put scalars out front, so let's go ahead and put the scalar 2t out front. And then we could even multiply through by that. So you'll have what? 4t squared cosine t squared, comma, negative 8t squared sine of t squared, comma, and then negative 4t squared sine of t squared. So there's the result of computing the derivative of v of t squared. All right, and then I'll let you do b and c on your own. Just use the rules as given in theorem 12.7. Just straightforward application of calculus, folks. Any questions so far? I'm going to move through this material fairly quickly tonight, unless you have any specific questions, because I've been in a little bit of pain, so I'm going to try to get home and take some medicine. I got a back issue going on right now, so. Higher order derivatives. Look, the second derivative, third derivative, fourth derivative, you just take those same order of derivatives for each of the components. All right, so no mysteries when it comes to calculating higher order derivatives. So if you want to take r double prime of t, for example, then that's just going to be what? X double prime of t, comma, y double prime of t, comma, z double prime of t. Okay, etc. So, for example, 4, we have r of t is equal to t squared, 8 natural log of t, and 3 times e to the negative t. First, second, and third order derivatives. Well, r prime of t is what? 2t, comma, 8 over t, comma, negative 3 e to the negative t. Second derivative. So we just move through here and calculate second derivatives like we know how to do. Negative 8 over t squared, comma, 3 times e to the negative t. Third derivative. So derivative of 2 is 0. We got what? Negative 16 over t cubed, comma, negative 3 e to the negative t. All right, so there's some higher order derivatives. Okay. Now, I wrote this down incorrectly, didn't I? This was supposed to be minus 2t, huh? That's okay. You know how to calculate derivatives. Moving along here. All right, we could also calculate antiderivatives as well as the definite integrals. So we'll see how to do that real quick. No mysteries here. You just go through and calculate the antiderivative of each of the individual component functions of the derivative, as well as there being your constant of integration, which is a constant vector. Right, so no surprises. Let's do an example here. Example number 5, integral of. Bad thing about this one is it's bad enough to have one hard integral for a normal Calc 1 or Calc 2 problem, but imagine now having 3 times the fun. Right? So here we have t over square root of t squared plus 2 I hat plus e to the negative 3t j hat plus sine of 4t plus 1 k hat. All right, we're going to calculate the antiderivative of this vector valued function. So like you say, we just integrate each of the individual functions. So first of all, the integral of t over square root of t squared plus 2. Yeah, what is that? Can anyone tell me? How do you calculate that antiderivative? Substitution, exactly. So what is the antiderivative of t over square root of t squared plus 2? Probably just the square root of t squared plus 2, huh? I hat plus, actually that'll be minus, what, 1/3 e to the negative 3t j hat minus what, 1/4 cosine 4t. So actually this will have to be a plus a negative 1/4 cosine 4t plus t j hat. K hat. Let me fix that k hat. It's supposed to be k hat there. Sorry about that. See, that's why we do our work in pencil. At least me, because I know I make mistakes from time to time. All right, so there it is. But we also have to remember that for each one of these anti-differentiations, there was a constant of integration. So you could introduce that constant of integration here, like a plus C1, plus C2, plus C3, or you could have it out here as a separate constant vector. Either way is fine. Whatever makes you feel good. Okay. All right, let's do another example here. Here we're going to find a vector valued function r of t such that r prime of t is equal to the e squared comma sine of t comma t. So in other words, we're taking the antiderivative of r prime. So we're given that r prime of t is equal to e squared comma sine of t comma t. But we're also given an initial condition that the initial position r of 0 is at j hat, which I could write at 0, 1, 0. So let's go ahead and compute the antiderivative. So r of t is going to be the integral of e squared comma sine of t comma t. Oh, t. See, that's why my mind cannot keep up with my hand. dt. So here we go. We have e squared t, comma, negative cosine t, comma, 1/2 t squared, plus some constant vector. Now let's set t equal to 0. When we set t equal to 0, the first part is 0. What is negative cosine of 0? Negative 1, okay. So that looks kind of suspicious, huh? And also we have 0. So what is happening here? So it was the antiderivative sine of t equal to negative cosine of t? Okay. Now, we still had a constant vector, huh? And that's supposed to be equal to 0, 1, 0, huh? Now, that c vector is equal to, oops, not equal, but plus, is a C1, C2, C3. C1, C2, C3. And set that equal to 0, 1, 0. So 0 plus C1 is equal to 0. So that means that C1 is equal to 0. We have negative 1 plus C2 is equal to 1. So what does that imply about C2? C2 must be equal to 2, huh? And 0 plus C3 is equal to 0. What does that imply about C3? That C3 must also be equal to 0. So therefore, R of t is going to be equal to e squared times t, comma, and then we have 2 plus negative cosine t for the y component. So we have 2 minus cosine t, comma, and then 1/2 t squared. So there is the position vector that satisfies those initial conditions, or this initial condition, I should say. Okay, so it's like just taking, finding the solution to a differential equation with an initial, it's like an initial value problem. Okay, and then finally, to take the definite integral of a vector valued function. Well, you compute the definite integral for each of the component functions. No surprises. Okay, moving along here, example 7. Suppose that we want to integrate from 0 to pi the vector value function I hat plus 3 cosine t over 2 j hat, then minus 4t k hat dt. So of course we know what to do, just integrate 1, which is t I hat, but we're going to evaluate t from 0 to pi, I hat plus, and then the antiderivative of 3 cosine t over 2, what is that antiderivative? All right, so that should be what? 6 sine of t over 2. Evaluate it from 0 to pi, j hat. And then what? Minus 2t squared. Evaluate from 0 to pi, k hat. Now for the first one, we have t evaluate from 0 to pi, gives us pi, I hat. Now sine of pi over 2 is 1, right? So we have 6 times 1 minus 6 times the sine of... What is the sine of 0? 0, right? So we have 6 times 1 is 6. So we have plus 6 j hat. And then minus 2 pi squared k hat. So there. The result is a scalar vector. Just like for a scalar function, when you integrate it, the result is a number, which we interpret to be the area under the curve from A to B, right? Same idea. Okay, so that's it for section 12.6. Let's go ahead and take a 10-minute break. And then we will then talk about projectile motion. Okay, moving along to the next section. Now we're going to talk about trajectories of particles through space. And in particular, projectile motion, which is the most common sort of motion. Because after all, what's more natural than to throw something in the air, and what sort of motion does it do? It basically is parabolic. But think about all the forces that are involved with this thing that you just flung in the air as it goes up and then comes back down in this parabolic arch. So, and that's actually kind of a difficult problem if you are interested in, lobbing ammunition downrange. So if you are into like field artillery, for example, and you shoot this projectile out of a howitzer, 20 miles down range, think about all the forces that act on that projectile, not the least of which is wind resistance, right? Or air resistance, and then the forces of these winds that buffet it, and then the imperfections on the shell. So the resistance caused by that, the spin of it, because in a howitzer shell there's rifling in there, so there's going to be a spinning. So what happens if you've ever, threw a baseball at high speed? What happens when there's a spin on it? It curves, right? So when you have this artillery shell going through air and it's spinning quite rapidly, it's going to curve as well, right? And then, not the least of which, you have the rotation of the Earth, which might not seem like a big deal because we can't feel it, can we? But during that period of time that projectile is in the air, minute or two, the Earth is going to move, right? Now, if you're shooting from north to south or south to north, then there's going to be some horizontal displacement, huh? You're going to be either shooting to the left or to the right of your intended target, right? Or if you're shooting to the east or to the west, then you're either going to be shooting long or shooting short because of the rotation of the Earth. Or if you're shooting at some other angle, it'll be a combination of there too. All right, so anyway, so that's an interesting problem to study. Of course, we're not going to really study it in this class, but it's just something to think about. How can we study particles? Now, what I mean by particle, anything that has mass, right, that as it travels in three-dimensional space. And we can use these three-dimensional vector value functions to assist us with that. All right, so, and I don't really mean for this to be a physics lesson, but unfortunately, calculus and physics are linked. So you learn a lot of physics as you learn calculus, and in physics class you learn a lot of calculus along the way. So we've got this trajectory modeled by a three-variable vector value function. No, not three-variable, three-component vector value function. Functions of t. And here we go. We've got this black curve in three-dimensional space. And remember that the velocity, which is r prime, is going to be parallel with the direction of travel for any specific time. So as we go through space, your velocity vector will point in the direction of travel and be tangential to the curve. What do you suppose acceleration is? Well, it's the derivative of the velocity function, right? Or in other words, it's r double prime, the second derivative of the position function. Okay? So we should be able to, at each point along the curve, be able to calculate the velocity and calculate the acceleration. Now, the velocity, like I've said many times now, is always going to be tangential to the direction of travel. But what direction does the acceleration point? What is the second law for Newton? What does Newton's second law indicate? It has to do with the relationship between the sum of the forces acting on an object and the mass and the acceleration. And what is that equation? F is equal to ma. So meaning the force, the overall force that an object experiences is the product of its mass and acceleration. So is mass a vector value function? No, it's just a scalar. But acceleration is a vector value function. And so therefore is force. Force is just a scalar multiple of acceleration. So force and acceleration will be pointing in the same direction. And indeed, when you see this curve, this happens to be a two-dimensional curve, but notice that the acceleration points in the direction that the curve is bending. So imagine that there's some sort of force that this particle is experiencing pointing to the left here in the direction of the green vector. So that you can see that the trajectory is bending in the direction of the acceleration vector, and even more so as you go further along at time 1 compared to time 0. So that's something to keep in mind, is that the acceleration vector will point kind of on the inside of the bend of the curve. Does that make sense, folks? Kind of? Can you visualize it? So for our motion in space, modeled by a position function, r of t is equal to x of t comma y of t comma z of t, for time non-negative. The velocity is given by r prime. The speed is the magnitude of r prime, meaning the magnitude of the velocity vector. The acceleration of the object is the second derivative of r, or the first derivative of the velocity vector. So here's kind of an example. This is example number 1 that we'll just take a look at. This shows, for the black circle that goes counterclockwise, the trajectory of r of t in 2 dimensions of 3 cosine of t, comma 3 sine of t. And in particular, we're looking at the time interval 0 to 2 pi. So we start off here at t equals 0, and as t increases from 0 to pi over 2, we go from here at 3 o'clock up to the 12 o'clock position. And then as t goes from pi over 2 to pi, we go from 12 o'clock to 9 o'clock. And as t goes from pi to 3 pi over 2, we go from 9 o'clock down to 6 o'clock. And then as we go from 3 pi over 2 to 2 pi, we go from 6 o'clock back to 3 o'clock. So just that's it. That's just the trajectory of that curve. It's just a certain length, finite length. Now, if we take the first derivative of r, so we compute r prime. R prime is going to be, well, the derivative of 3 cosine t is going to be what? Negative 3 sine of t, comma, derivative of 3 sine of t is 3 cosine of t. And if you were to evaluate v prime, or r prime, which is v, if you were to evaluate this at, at t equals 0, pi over 2, pi, 3 pi over 2, you'll see that you get these velocity vectors that are, parallel with the direction of travel. So this is what r of 0 would be. R prime of 0, I should say, would be what? 0, comma 3. This is 0, comma 3. This velocity vector. At pi over 2, all right, you have negative 3 and 0. So there's negative 3, 0, and so forth. Now, go ahead and take the second derivative. Oh, I'm sorry. Yeah, second derivative. Let's go ahead and calculate second derivative. R double prime. Because I want to get the acceleration here. You get what? Negative 3 cosine of t, comma, negative 3 sine of t. Yeah. So there's your acceleration vector. And if you were to evaluate r double prime, which is a of t, at t equals 0, pi over 2, pi, 3 pi over 2, and you get these yellow vectors, and they all happen to be pointing inward toward the center, in this case. Which should make sense, because this circle is always bending to the left. So that implies that there's some sort of force that's kind of pushing it always inward. Remember, the force vector is parallel with the acceleration vector. So when you have this sort of centripetal motion going around and round and round, that means that the acceleration vector is pointing inward. So one way to visualize this is just to get a rock, tie some rope around the end of it, and then swing it around. Now, you have an outward force on the rock, the centrifugal force, right? Is it really a force? But it's like a pseudo force, huh? But there's a force, exerted on the rope inward to balance out this tendency of the rock to fly outward, huh? So that tension on the rope is this force vector pointing always toward the origin. All right, so here we've got example number 2. Now let me just talk you through this. For example number 2, we have a little r of t given by t comma t squared minus 4 comma 1/4 t cubed minus 8. And we've got big R of t, which is t squared comma t to the 4th minus 4 comma t to the 6th over 4 minus 8. Now, hopefully you're following along in the textbook as well. But as you look at these two trajectories, these two different R functions, what do you notice as to the relationship between the two of them? Those of you who are looking, this is example number 2 on page 839. What do you notice between little r of t here and big R of t? What's the relationship between them? Anybody? Yeah, well, it's this, wherever you see t here, in a little r of t, replace little t by t squared, huh? And you get this one. Otherwise, they're the same function, huh? So, if you replace t by t squared, and then you let t go from 0 to infinity, do you get the same curve? Do you get the same trajectory? And the answer is yes. The same path will be traced out. But velocities will be different. Now, let me just make the observation that the velocity vector is made up of what? The scalar piece and its direction piece. Huh? The scalar piece is the speed, right? And the direction. The direction indicated by the relationship of the components to each other. Now here at t equals 4, you happen to be at this position 4, 12, 8 with this first function, a little r of t here. That little r of 4 is equal to 4, 12, 8. But at big R of 2, you're at the same point. So what does that tell you about big R? It's faster, right? It has a greater speed, same direction, right? But the magnitude of big R prime will be larger than the magnitude of little r prime. Does that make sense? So if you were to calculate, and you could do it on your own, magnitude of big R prime and compare it to magnitude of little r prime, compare them. Actually, we can compare them right here by looking at the graph. Here's the speed of little r, which is in green. Here's the speed of big R, We're comparing the speeds. Huh? Blue, the speed for big R increases much more quickly, huh? So what this is saying is that if you have this particular path in 3 dimensions and you want to adjust the speed, then you can just, create some function of t which will slow it down or speed it up. So if you want to speed it up, replace t by t squared or t cubed or whatever it is that you want to do to get the speed that you desire. If you want to slow it down, you could replace t by t over 10, square root of t. You know what I mean? All right. Now, I want to talk about circular motion. Again, we already had a small discussion of it already. Now, circular motion, there's a certain relationship between R of t and v of t, between the position and the velocity. Not just once, but throughout its entire trajectory. So one way that you could tell that you have motion on a circle or sphere in 3 dimensions is if you were to take the dot product between the position and the velocity, and you always get 0 for all values of t. Why is that true? Well, do you notice that R of t is always going around in a circle, huh? So is the magnitude of R, is that ever changing? The direction of R is changing, but not the magnitude of R. Okay, so the magnitude of R is constant. Okay, so that means that the magnitude of R, quantity squared, would also be some constant, huh? Now remember, R is a function of t. Now what happens then if you were to take the derivative of, and I'm going to write R magnitude squared as magnitude R times magnitude R. And the derivative of a constant on the right-hand side there is equal to 0. So, of course, then you can use the product rule So there, I used the product rule. But then this is going to be 2 times R prime t times R t, magnitude thereof, is equal to 0. So what does that say the relationship between R prime and R? We have a good discussion of this. Now, another way to look at magnitude R of t squared is to take the dot product as well. So it's probably not very clear right here by looking at that R prime and R orthogonal to each other, but we could also take a look at that if magnitude r squared is equal to some constant, magnitude r squared can be thought of r of t dotted with itself. That means that the derivative of this dot product is equal to 0. And then we could use the product rule for dot products. But then this would be 2 times r prime of t dotted with r of t is equal to 0. And of course that means that the velocity dotted with the position function is equal to 0. So when you have circular motion, the magnitude of r as a constant, which is the same thing as saying, is that the velocity and the position of functions are orthogonal to each other. Not just for a single or a couple of values for t, but for all values of t. Okay, so you might be asked the question, here is the position function r in 2 dimensions maybe. Same discussion goes for vectors in 3 dimensions. And the question is, does this describe motion on a circle for 2 dimensions or on a sphere for 3 dimensions? The easy way to tell is to take the dot product with r and its velocity. And if that dot product is a constant 0, then that would tell you that you have circular or spherical motion. Spherical motion means you have motion, 3-dimensional motion on the sphere for 3 dimensions. Just take the dot product of r and v. See what you get. If you got 0, then the answer is yes. Okay? Moving along here. So we just had this discussion. Motion on a circle or a sphere, same thing as saying as r dot v is equal to 0. Moving along here. Now, we want to get to the point where, so example 3 is just an example of what we just did. We want to get to a point where we talk about projectile motion. We'll do that here in a minute. Let's just do one of these examples from example 3. Example 3, we have r of t is equal to 3 cosine of t I hat plus 5 sine of t j hat plus 4 cosine t k hat. And let's answer the question, does this object whose motion is described by this vector valued function, does this object move on a sphere? We won't do part B probably, but does it move on a sphere? Well, let's calculate the velocity v of t, and that's going to be what, negative 3 sine of t I hat 5 cosine t j hat negative 4 sine t k hat. and then take the dot product of r with v. Now, we're talking 3 cosine t times negative 3 sine t. So you get what? So, hold on here. So this is just going to be a scalar here, so we multiply and add. So we have what? Negative 9 sine t cosine t plus 5 sine t times 5 cosine t. So you got 25 sine t cosine t. And then we have what? Negative 16 sine t cosine t. So minus 16 sine t cosine t. So you got negative 9 plus 25 minus 16 sine t cosine t, which is 0. So because of the fact that r dot v is equal to 0, the answer is yes, this object moves on a sphere. What would be the radius of this sphere? What would be the radius of the sphere? Well, the short answer is to take the magnitude of r, huh? So go ahead and take the magnitude of r. So you have what? 3 cosine of t squared plus 5 sine of t squared plus 4 cosine of t squared. Now, so you have 9 cosine squared t plus 25 sine squared of t plus 16 cosine squared of t. So you're going to be left with 25 cosine squared t plus 25 sine squared t. Pull out the 25, it becomes 5 on the outside. Leaves you with cosine squared of t plus sine squared of t, which is 1. So in other words, you're left with 5. So 5 would be the radius of the sphere over which this object moves. And if you wanted to find the velocity and the speed of the object, you can just simply find the magnitude of v for your speed and take the derivative of v to get your acceleration. Okay, moving along here. Let's talk about projectile motion now, one of my favorite topics. For about 7 years in the Army, I was a field artillery officer, so this was one of my topics of specialty. Except for the fact that we didn't really do any theoretical stuff. It was almost all done by computers in the modern age now, and with slide rules and stuff. So here's the idea here, is that at some starting position in two-dimensional space, we have some object that we're going to launch into air. Now imagine that this is just in the two-dimensional realm. We'll do a three-dimensional object here in a few minutes. So we launch this object in a certain direction as indicated by the initial velocity, which also has information about the initial speed, which would be the magnitude of that initial velocity. So the initial velocity gives you speed and direction, huh? And then once you know that initial velocity, then the rest of that motion is determined by gravity, huh? But you already know gravity, so really the entire trajectory of that projectile is determined by the initial position and the initial velocity. And we could even make it simpler by actually putting the initial position at the origin of our coordinate system. So, in that sense, the entire trajectory is determined by the initial velocity, by the direction and the speed. We'll get there. We'll take first things first. Now, so we're going to consider an object moving on the plane, XY plane, with a certain horizontal axis and the vertical y-axis. So horizontal indicating the ground, essentially, and the y-axis indicating the vertical direction going away from the ground. Subject only to the force of gravity, so we're not considering wind or it hitting a bird or anything as it goes up in the air and comes down in pressure. And we're not concerned about the movement of the earth or any gravitational fields or anything. All right? Now, given an initial velocity v of 0 with components of u sub 0, v sub 0, and initial condition, initial position r of 0 given by x sub 0, y sub 0, the velocity of the object for t greater than or equal to 0 is given by, now u sub 0 comma negative g t plus v sub 0. Where did they get that? Where is that? Well, so let's talk about that. It really comes down to solving an initial value problem for the differential equation. Starting off with the acceleration due to gravity, using Newton's second law. So we have acceleration, which is basically given by 0 comma negative g. Right, that's just basically saying that the acceleration due to gravity is going in the negative y direction. I think we've got a picture of that here. Either here. So here's a picture of that. So because the force vector is given by 0 comma negative mg, that means the acceleration is 0 comma negative g. And then we integrate acceleration to get velocity. So there, we just integrated a and t to get your velocity vector. But what we need is for the initial velocity to be equal to u sub 0 comma v sub 0. U sub 0 comma v sub 0. So there we go. So this is what proves to us that the velocity of that object as it goes up and then down along its trajectory is given by u sub 0, which is the x component of the velocity, and then we have v sub 0 minus g of t. So there's the velocity function. And then we can go ahead and integrate again to get r of t. So integrate with respect to t, you have u sub 0 plus c sub 3, constant of integration. And then we have what? V sub 0 t minus I didn't mean to put the t in parentheses there. So we're going to have minus 1/2 g t squared, and then plus some constant of integration. There we go. Now, we set this t equal to 0. C3, comma C4, and R of 0 will be at x sub 0, comma y sub 0. So then we have R of t is equal to, because C sub 3 is equal to x sub 0, C sub 4 is equal to y sub 0. So that means that we have x component of R being u sub 0t plus x sub 0. So x sub 0 plus u sub 0t, comma, write that better, t, comma, and then we're going to have y sub 0 plus v sub 0t minus 1/2 gt squared. So the x sub 0 plus u sub 0t is going to be the x component of motion. And the y sub 0 plus v sub 0t minus 1/2 gt squared will be the y component of motion. You can kind of think about each one of those components as functions of t will give you the x coordinate as function of t and the y coordinate as a function of t. So if you want to know what are the x and y coordinates at any point in the trajectory, just evaluate each one of those functions with that particular value for t that you have in mind. Okay, so there I just kind of established the R equation for you, the R function. So this is what it looks like. You hit the ball here at home plate if you're playing baseball. And once you have established that initial velocity, then the whole trajectory is determined. It'll go up and it'll go down. Let's take a look at example 5. Sorry, example 4, I should say, example 4. Yeah, sorry, this is example 4. Example 4, part A. We have a baseball that's hit from 3 feet above the home plate. So that means that the initial y component is 3, x component is 0 for the position. With an initial velocity given by, v sub 0, 80, 80. So with this given information, let's go ahead and write our position function. So R of t is going to be equal to, now, u sub 0t plus x sub 0. Now, x sub 0 is 0, and u sub 0 is 80. So we have 80t as the x component of motion. Now, for the y component, we have negative 1/2 gt squared. Now, we'll leave g as it is. It's some constant. It's the acceleration due to gravity. Plus v sub 0. V sub 0 is 80. And y sub 0 is 3. So there's our position function. Remember that 80t, that is basically your x coordinate as a function of t. And the negative 1/2 gt squared plus 80t plus 3, that is the y component or the y coordinate as a function of t. Now, if you want to know the velocity of this baseball, then all you need to do is compute the first derivative. So you have 80, comma, and then you've got negative gt plus 80. There's the velocity of the baseball as a function of time. Notice that the horizontal speed is constant. That's one of the hallmarks of projectile motion, is that the horizontal component has a constant speed. So for the entire time that that ball is in the air, it's going to be going, 80 feet per second horizontally until it hits the ground. Now, the vertical motion velocity / speed is given by the negative of the acceleration due to gravity times t plus 80. Now, for part B of this problem, and again, this is example 4, show that the trajectory of a ball is really a segment of a parabola. Well, that could be demonstrated by just simply taking a look at, you've got basically parametric equations where you have x is equal to 80t, and you have y given by negative 16t squared plus 80t plus 3. Because you have a pair of parametric equations, you can eliminate the parameter t. By the x equation, you can solve for t by writing t as equal to x over 80, and then substitute x over 80 in for t in the second equation, so that now you have y as a function of x is equal to negative 16 times, and in place of t you have x over 80, so you have x over 80 squared plus 80 times x over 80 plus 3. And then, of course, you can simplify that. But you notice that you have y as a function of x, and in particular, that function of x is a second-order polynomial, the graph of which is a parabola. So this is what demonstrates that the trajectory is parabolic in nature. Okay? Does that make sense, folks? Stop me if you have any questions about anything. So example 4, part C, assuming a flat playing field, how far does the ball travel horizontally? It will travel horizontally until it hits the ground. When will it hit the ground? Well, there's a couple ways that you could solve this. How far does the ball travel horizontally? So you have y as a function of t. Let's go back to y as a function of t. Now, y as a function of t is negative 16t squared plus 80t plus 3. Now, the ball hits the ground when y is equal to 0. So you set the second order polynomial, second degree polynomial equal to 0, and solve for t. What is the handy tool that we have at our disposal from algebra class to help us solve this equation? And it starts with Q. Quadratic formula, exactly. So, And so quadratic formula. So you have t is equal to what, negative 80 plus or minus the square root of b squared. So you have 80 squared minus 4 times negative 16 times 3 over 2a. So 2 times negative 16. Now, you will, and you could check this on your own because I have a supreme confidence that you can do this. But you get two solutions when you do this, when you take the plus and the minus. When you do the minus piece, you get what? Negative 0.04 as one solution. When you do the plus piece, you get 5.04. 5.04. As in 5.04 seconds after the ball is hit, the ball will hit the ground. It will have a height of 0. So then what do you do with this value for t? 5.04 seconds. Well, you plug it back in to the x equation, as in how far did this object travel horizontally in 5.04 seconds. So we'll take x of 5.04 seconds. Now x of t is 80t, so we have 80 times 5.04 seconds, which gives us what? About 403. As in, this object, as in the baseball, traveled 403 feet horizontally. You could have just as well have gone back to this equation from part B and set this right-hand side of this equation and solve for x, and you have got the same answer, 403 approximately. Okay. All right. Any questions on how to do this one? So you know the range. This is a range problem. The range basically means how far did it travel. For part D, part D is asking us, what is the maximum height of the ball? So the ball goes up, it comes back down. Now we know that horizontally the ball is going at 80 feet per second, but vertically the ball starts off at 80 feet per second, but it slows down because we have the minus gt, right? Because the acceleration due to gravity pushing against it until it finally reaches its maximum height, then it reverses direction, and then your y prime is now negative. So at what value of t will y be at its maximum value? That would be at the precise point where y prime is 0. Now we computed the velocity vector, didn't we? Which means that we've got y prime of t, and that's negative 32t plus 80. Where did the negative 32 come from? Because we're using g to be approximately 32 feet per second squared as the acceleration due to gravity. Now, in some contexts, you could use 32.2, right? So then you set y prime equal to 0, solve for t. So t would be equal to 80 over 32. And what does that work out to be? So 2.5. Bless you. So after 2.5 seconds, the baseball will reach its maximum height and descend And then you plug that value for t into your y function. So you take y of 2.5. Now your y function is your negative 1/2 gt squared plus v sub 0 t plus y naught. And what was that in our... So that was equal to negative 16t squared plus 80t plus 3. So now you plug in 2.5 for t. So you go negative 16 times 2.5 squared plus 80 times 2.5 plus 3. And that should yield you 103 feet, approximately. So the maximum height of this ball right up here at the top is 103 feet above ground. So we know its range, we know its maximum height, so do we know everything that there is to know about the trajectory? Sure. Final question would be, will it clear the fence? So if we go back and take a look at this picture here, there's a fence over here. And according to the problem, this is a 20-foot fence. So will the ball go over the fence or not? Now, how far out is that fence? It's at 380 foot, huh? So one thing that we could do is take a look at this equation right here, where we have y as a function of x. So we can go ahead and evaluate this at x equals 30. What is the height of the ball when you are out horizontally at 380 feet? So just replace x by 380. So now this is just an algebra problem. So what does that work out to be? Well, I think it works out to be about 22 feet. So the height of the ball when you're 380 feet away is about 22 feet. So definitely the ball will clear the fence. Okay, does that make sense, everybody? All right. So let's take a quick 5-minute break. And when we come back, we'll finish this up, okay? This discussion of projectile motion. Let's go ahead now and establish more of a general set of equations for projectile motion, where this time we have the origin at the point of departure for a projectile. All right, and we're given an initial speed. So we have x, we have y, and so we're told initial speed, and we're given an angle. Actually, they call it alpha, don't they? An angle of inclination So if the origin is where the point of departure is, or you might have an initial height, h sub 0, but the entire trajectory is determined by alpha and the speed. And that's it. So let's kind of go through there without spending a whole lot of time on any one thing and establish some equations to help us deal with projectile motion problems. So we start off again with acceleration being given by 0, negative g. Now, as you read through that section that starts with range, time, maximum height on page 844, we are assuming that the motion of the object begins at the origin. So there is no initial height except at 0, right? Okay, so then again, you go ahead, take the antiderivative of acceleration, and what does that give us? That's going to give us our x component of the initial velocity for the this first piece. So that's going to give you the initial speed times the cosine of alpha, alpha being the angle of inclination. And then for the y component of velocity, you're going to have the initial speed times the sine of alpha. That's the y component of the initial velocity minus gt. And then integrate one more time to get x of t, so that you have the, no, not x of t, sorry, r of t. R of t, sorry about that. R of t, now the x component of the position is going to be just the antiderivative of the x component of the velocity. So then the initial speed times cosine alpha is just a constant. So we'll have, so the initial speed times cosine of alpha times t, comma. Now there is no initial height, so we'll just have initial speed times sine of alpha times t minus 1/2 gt squared. Okay? So if you are given that, you know, your object was launched from the horizontal, so from the ground level, and you're given the initial speed and the angle of inclination, then you can use this equation right here to generate your position function. And then you can answer all kinds of questions. So number one, time of flight. Time of flight, basically, how long does it take for the object to go up and down? So if you were to set this y component equal to 0, of course, one solution would be t equals 0. The other solution would be when the initial speed times the sine of alpha minus 1/2 gt is equal to 0. And then, of course, then you could solve for t by adding 1/2 gt to the other side and then multiplying both sides by 2, subtracting, or not subtracting, but dividing both sides by g. So that means that you have t, which, by the way, they call capital T, so why don't I call it capital T? The time of flight is equal to what? So initial speed times sine of alpha times 2 divided by acceleration due to gravity. So there's the time of flight. So you want to know how long it takes for the object to go all the way up and then all the way down? Well, you need to tell me the speed, you need to tell me the angle of inclination, and of course we know the acceleration due to gravity, either in, we're dealing with the USCS or the SI, all right, system of things. All right, so this kind of shows us the components that we're talking about. Alpha was that angle of inclination, the v sub 0, it was that velocity vector, the magnitude of which was the speed, the initial speed. So you saw that we had decomposed that initial speed into horizontal and vertical components by multiplying by cosine of alpha and sine of alpha, respectively. All right, now let's talk about number 2, which is the range. The range is where, you know, how far horizontally does it go? Well, that's simple, because you evaluate the x function at where the t is equal to the time of flight. So that means, well, no, x of t, though, is equal to the speed, the initial speed here, times cosine of alpha, and then times the time of flight. But the time of flight is going to be hold on here, I lost my thought here, is 2 times the initial speed times sine of alpha over g. So we have 2 times the square of the initial speed times sine of alpha, cosine of alpha, over g. Now 2 times sine of alpha, cosine of alpha is the sine of 2 alpha. So we could write this as initial speed squared times the sine of 2 alpha. Because of the fact that 2 times the sine of alpha, cosine of alpha, is equal to sine of 2 alpha over g. Now, what is the angle alpha which will maximize the range? Yeah, exactly. So that's kind of a common sort of, you know, question asked of beginning physics students. And all you need to do is take a look at sine of 2 alpha. Now the sine function varies between 0 and 1. And so on the interval from 0 to 2, or 0 to pi, I should say, on the interval from 0 to pi, the sine function is going to be maximized when the angle that you take in the sine of is 90 degrees, or pi over 2. But 2 alpha is pi over 2 when alpha is equal to pi over 4, huh? So max when alpha is equal to 45 degrees. Also, you could just take the derivative of x with respect to t, or with respect to alpha, actually. you could take x prime of alpha and set that equal to 0 and solve for alpha. You'd still get alpha equals 45 degrees or pi over 4. Okay? But of course, you can evaluate it for all these other initial angles as well. And believe it or not, you get just as much range at alpha equal 20 degrees as you do for alpha equal 70 degrees for the low angle and a high angle trajectory. So one of our favorite things to do in field artillery firing exercises is to what we would do is we'd shoot this high angle projectile and then crank down the howitzer and shoot at the same target with the low angle, and to time it so that both rounds hit at the same time at the same location. It's always a fun exercise. So but why should it be, though, that we can find such an angle that will that when you take that angle and subtract it from 90 degrees, that you have the two trajectories ending up at the same location? Well, and it's because of the fact that when you take a look at sine of 2 alpha, that the sine is going to be the same for alpha as well as pi minus alpha. So sine of 2 alpha is the same thing as the sine of 2 times pi minus alpha. So there's a nice little trigonometric identity for you to verify. Okay, moving along here. Now, part 3 of this little exercise here has to do with an equation or formula that will calculate our maximum height. Now, our maximum height is going to happen at a time halfway between when the object is launched and the object hits the ground, right? Now, we saw that the time of flight was equal to 2 times initial speed times the sine of alpha over g. That was our time of flight. So the max height is going to happen at t over 2. Does that make sense? Because of the symmetry of that trajectory. I mean, if you look at that parabola here, if it takes capital T seconds to go from the point of launch to where it hits the ground, then it should take t over 2 to get to its maximum height. So if you want to find the maximum height, then you evaluate y at half of the time of flight. But half of the time of flight will just be the initial speed times sine of alpha over g. So y of t2, now y, remember, is negative g over 2 times t squared. Now, t squared here then is going to be initial speed squared. Well, I'll just write initial speed times sine of alpha over g, quantity squared, and plus initial speed times sine of alpha times t. So again, we have initial speed times sine of alpha over g. And then look, it's just an algebraic exercise now here. You've got V naught, or the speed, I should say, times sine of alpha, times this stuff over here on the right. So, and so when you combine this piece together with this piece, what do you get? You get speed times sine of alpha quantity squared over 2g. So there's the little formula that tells you what the maximum height is. You just plug in the initial speed times the sine of the angle of inclination divided by 2. Oh, and you square that product, and then you divide by 2g. So, folks, all I'm doing is I'm just establishing some formulas for you. So now you've got the formula for the time of flight you've got the formula for the maximum range, and you've got the formula for maximum height. Okay? And all of these are in the textbook as well. And here they are summarized as well. Pretty handy things for you to put on your sheet of notes, huh? By the way, when it comes to take the test. Not that I encourage memorization only to do a brain dump later, because it's always nice to be able to derive from first principles all the formulas that you need. But it's always nice to have the formulas handy as well, huh? All right. So we could do flight of a golf ball if we wanted to. It's just a matter of plugging in the numbers in. So let's do a couple of these. But I'm not going to do example 6. You can if you want on your own. But let's do example 5, or at least a couple of these from example 5. Example 5, a golf ball is driven down a horizontal fairway with an initial speed of 55 meters per second. So horizontal fairway, that means that the ground is level. So the initial speed is 55 meters per second, and the initial angle, alpha, is equal to 25 degrees. The T height is negligible. Only assume it's gravity that's working on the ball, no other forces, no wind or anything. So for part A, how far does the ball travel horizontally? Oh, they want us to calculate the range. The range is initial speed squared times sine of 2 alpha over g. Now initial speed is 55, so we'll just plug in 55 squared times the sine of 2 times 25 is 50 degrees divided by, and because we're dealing with meters per second, we'll use 9.8 meters per second squared as our acceleration due to gravity. So you plug that in, and you're left with about 236 meters as the range of flight for the ball. They're asking, when does it land? As in time of flight, huh? So the time of flight is 2 times the initial speed times the sine of alpha over g. So again, it's a matter of plugging in the numbers. 2 times 55 times the sine of 25 degrees over 9.8. And that's about 4.7 seconds. So there's the time of flight, and there's the range. Part B is to answer the question, what is the maximum height of the ball? Oh, okay, we've got the formula for the maximum height. And that's equal to initial speed times the sine of alpha. That product is squared divided by 2g. So, hey, folks, this is too easy. Just plug in the numbers and evaluate. So you take 55 times sine of 25 degrees, square that, and then divided by 2 times 9.8. And what does that work out? About 27.6 meters. Okay? Now, here, part C, though, is the one that takes a little bit of thinking. So let's just think about part C. At what angle should the ball be hit to reach a green that is 300 meters from the tee? So you think about that, but then all you need to do is just take the formula for the range and you set this expression for the range and set that equal to 300. Meters, right? And now you have the initial speed already at 55, and you know what g is, so all you need to do is solve for alpha. Okay? Which I know you know how to do because you all passed the trigonometry class or pre-calculus class. So all you need to do is solve for alpha. And so, you know, so it just works out to be there's two angles that will do the job. 38.2 degrees and 51.8 degrees. Okay? Now, if you are interested in the three-dimensional problem of projectile motion, I invite you to look at example 6. But I'm not going to really emphasize it. Let me put it that way. I won't ask you any questions on it. But, you know, I might give you an extra credit problem on the exam, though, involving it, in case you take the opportunity to work through this. Who knows? All right, so for those people who are interested in opportunities for extra credit, so there's the occasional problem that we do together in class. There's the occasional extra credit problem, usually 1 or 2 problems or more. Depends on how generous I'm feeling on the exam. Okay. And plus, if you really kick butt on the